When we put silicon atoms beside one another, since they have 4 electrons in their valence shell, they would share them with one another to satisfy the octet rule. Obviously, since all atoms are similar, therefore they have similar electronegativity, and so they form covalent bonds. Therefore, silicon would become stable and wouldn't have any free electrons that could move. Why do we care about electrons moving? Well, we said previously the net charge is the source of this new field that we call the electric field. And since atoms are normally neutral, so to have a net charge, we need to have electrons moving or electrons movement. The opposite also holds true, that having a non-zero net charge would create a field, therefore electrons would move. So in a pure silicon, not only we have zero net charge, but also we have zero free electrons. To understand the difference, we could first make an analogy. Imagine we have a pipe. If you have water in it, by giving it some slope, the gravitational field would cause the flow of water. Pay attention, it's not that we define the current of water as moving one molecule of water from the beginning to the end, because if that was the case, it would have taken more time for the flow to begin. But we see that almost instantly we have the flow of water. By tilting the pipe, we say we have a potential difference, meaning we have a change in height throughout the pipe, and therefore we would have water flow. We could define the current as the amount of mass that passes one cross section in 1 second. Actually, because I want it to be a good analogy between the water flow and also the charge flow or the current in the electricity, I would define the current as the amount of mass water that passes, because you would see the relation later that we talk about the charge as well. But intuitively speaking, even if we wanted to have a good measure of water flow, let's say that you just want to create an abstraction to give you a good measure of the water flow, you'd say for sure that a speed is what gives us understanding of how fast the water is flowing. But a speed of what? Of one molecule of water or one area? It's actually the speed of water in one cross section in the pipe. Let's quantify that. Obviously, we need to multiply the amount of water mass in one cross section by its speed. So if we say the mass of each water molecule is m of m, and we have n number of water molecules in one cubic meter, because obviously we don't know how much molecules we have in a pipe, but we have water molecule density, or the number of molecules per cubic meter, and we call it n. Based on these, the current would be equal to n m of m times a times the speed. So the first 3 terms, the n, m of m, and a, would give us the amount of water molecule mass maybe per one cross section, and v would give us its speed. Therefore, it would give us a good measure of the water flow. In fact, if we work out its units, you would see that the unit of I in this case would be kilogram per second, which is what we were after, the amount of water mass that passes in 1 second. So it gives us the amount of mass that passes in 1 second, which was our first goal. It actually doesn't matter what we are talking about. Current is always like that. As an example, for electric charge, we just replace n m of m with nq to get the amount of charge. Because if previously m of m was the mass of the water molecule and n was the water molecule density, in this case q would be the charge and n would be the charge density. So n times q times a would give us the amount of charge in one cross section times v, which is its speed. And if we work out the unit, you would again see that the unit of this current would be equal to coulomb per second, which just means that we could represent I equal to dq over dt.